Hello, class. This is Professor Daryl Fisher again, here to teach you, starting with or continuing with Chapter 2, the chemistry of life. Remember, we talked about um, the organization of life, and we started off with chemistry, molecules, atoms, molecules. Um, we started off at that level, which we're going to talk about that a little more detail in this chapter. Then we go from that to cells, which are the basic unit of life. That's the point where we call it life, is at the cellular level. And then we go to tissues, combination of different types of cells working together. Then we go to organs, which is multiple tissues working together to perform a specific function. Then we go to organ systems, and then eventually to organism. All right, so building our way up the ladder of organization in the human being, we're going to start off at the bottom, which is the chemistry of life. All right, so we start off with atoms and elements, 2.1. All right, so the desk that you have, your computer or tablet, or the chair you're sitting in while you watch your phone, when you're watching this video, it's all matter. Everything that has mass, occupies space, is known as matter. You can have solids like the desk, the chair, the human body. You can have liquids such as, water, soda, coffee that I'm drinking right now. You can have gas, the oxygen that we breathe, nitrogen. All of that is matter. All of those have a substance. They're matter. And what chemistry basically is the study of matter and the interactions that happen, right? We know that, for instance, water is a liquid, then it evaporates, becomes water vapor, gas, and then it rains back down onto this earth. So, we study those interactions. We know that your body needs water to be able to burn fat. Part of the equation for fat burning in your body, it requires water. We know there's a bunch of chemical reactions that happen in your body at all times. That's some of those chemical reactions is called metabolism, right? So we want to study the chemistry, study how the liquids, the different liquids, the solids, the gases, all the different matters interact in your body. We really want to, in and outside of your body. The smallest unit of matter, remember we said the smallest unit of life is the cell, so don't get that confused. The smallest unit of life is a cell. An atom is not considered alive. You can go back to chapter 1 to see what we designate as living and non-living. But an atom is not designated to be alive, but it is considered the smallest unit of matter. And remember, when we start off with atoms and matter, we're not talking about things that are living yet, even though they are parts. They help us build up things that are living. We all have carbon, nitrogen, oxygen in us right now. Them by themselves, oxygen by itself is not alive, but inside my body, it helps my body to be alive. Okay, this can be a little bit confusing when we talk about that. But the smallest unit of matter is the atom. It contains the original properties of a specific element, okay? And it's made up of even smaller structures called the subatomic particles, right? So the smallest unit of oxygen, if you want to get oxygen down to its smallest unit, it would be an atom of oxygen. That would be the smallest unit of oxygen that you could get to that would still have the properties of oxygen, okay? An atom has a nucleus, which has protons and neutrons, and it also has electrons which surround the nucleus, float around the nucleus. And hopefully you've all taken some kind of chemistry class. If you haven't, and this sounds foreign to you, you can always set up a meeting with me to go back over it, and we can talk about it in a little bit more detail. But hopefully you have some kind of background in chemistry, and this is not all brand new. All right, so we're going to go through atoms and their atomic structure. So we have, making up of an atom, the smallest unit of matter, the atom. We have protons, which have a positive charge in the central core and the nucleus of the atom. You see here, these positive elements are protons. We have neutrons, which you see a little zero. That means no charge, slightly larger than protons. We have electrons, which have a negative charge, which float around on the outside, right? So that's what makes up an atom. Atoms are electrically neutral. That means they have no charge. The reason why they're electrically neutral is because the positives balance the negatives. And so if you have 6 positives, protons, six negative electrons, then the net charge is 0. Therefore, we can say atoms are neutral, electrically neutral. All right, hopefully that makes sense. We have what we call electron shells when we talk about atoms. Right, so we have the first, so you see these electrons that float around. The electrons generally balance the protons so that we have that electrically neutral charge, right? But they exist in shells. So in the closest shell to the nucleus, you have generally 2 electrons. Then in the second shell, you have 8 electrons. And the third shell is satisfied with 8 electrons, electrons. You can, so that will give you a, you could have, like I said, like I have listed here, that should be 8 electrons, not 18 8 electrons, and satisfied with 8 electrons. You generally want 8 electrons on the outside, but we're going to talk about how when you have bonding, how that can change, and we'll talk about that in a second. Some atoms may have more than 3 shells. You can also have 4 shells, depending on the atom. But generally, what we're going to talk about when we talk about the elements that are vital to life: oxygen, hydrogen, nitrogen, sodium. What else? Carbon. The ones that are vital to life, we usually won't have more than 3 electron shells, right? So that's generally what you have to worry about. Not worry about, what you have to know, right? And we'll talk about this in more detail coming up. All right, so atomic number. Hopefully you've all seen what we call a periodic table, that a listing of all of the elements that we know of in the world so far. Now they have added to it. They add to it every now and then when they discover something new, but for the most part, it's been pretty standard for a long period of time. Oxygen has been oxygen for as long as we've known. That's not going to change too much. Things like that. So with each element in the periodic table, we have an atomic number. Right? Atomic number is the number of protons in the atomic nucleus. Remember, from this, protons are in the nucleus, positively charged. Remember that. So the number of those protons, and that defines every element. Now, if we know the number of protons, we generally know the number of neutrons and electrons. All right, but we stick with atomic number being the number of protons. Element is a substance that cannot be broken down into simpler substance by chemical means, cannot be broken down. Each element is made up of atoms with same number of protons. Right? So we group those into what we call a periodic table of elements, and I'm going to show you that diagram soon, and so you'll see that, and hopefully that'll make more sense. But periodic table is just basically a listing. So we start with number 1, hydrogen, number 2, helium, and 3, 4, 5, 6, all the way down based on the number of protons in the nucleus. So how many protons it has basically decides what it is. And that's pretty much not gonna change. And so we can list those by their atomic number, and then we also give them a name as well. We start off with 1 and we just keep going up. certain groups on the period, certain groups are organized by certain properties, and then we also have a chemical symbol. Right? So this is what we've been talking about when we talk about periodic table. Hopefully everybody has seen this before. Hopefully this is not brand new, but still, when we start with hydrogen, 1, that means it has 1 proton and 1 electron generally, and 1 neutron, right? And then we have helium, 2. That's right. So those 2 are 1 and 2. Then we go on to the next line, lithium, 3. And these are going to be very important. These ones listed as major elements. We see the orange, so hydrogen, major element, H2O, hydrogen, 2 hydrogens and an oxygen, H2O, that makes water. Obviously, water is the most abundant. Water, no, not, I didn't mean to say obviously, but water is the most abundant molecule in the body. So very important. Anything with that. So the 2 elements that make up water, hydrogen and oxygen, are going to be very abundant in the body. Those are considered major elements. Carbon. Carbon is a building structure in the body. You find it in the body as well as in the earth. Nitrogen is also they're aminos. So all through your DNA is the element nitrogen. So very common in the body. Also, you'll see the ones that are in green. We're going to talk about those as well. Sodium, magnesium, Na, sodium, Mg, magnesium, K, potassium, Ca, calcium. Very important. Everybody, when they think of calcium, probably think of bones, but we're also going to see calcium in the muscles. Sodium is very important for our nervous system. P, phosphorus, S, sulfur, Cl, chlorine, right? NaCl, Na, sodium, Cl, chlorine, NaCl makes salt, which is very important in the body. All right, and then you'll see some of the other trace elements as well, and we're going to talk about those too. All right, so this is the periodic table organized by the atomic number, which equals the number of protons. So if I go to oxygen, for instance, O is oxygen. It has an 8 above it. That means it has 8 protons. That means it also has 8 electrons. And in the case of oxygen, 8 neutrons. Okay, pretty simple. Like I said earlier, the human body is made up of 4 major elements: hydrogen, oxygen, carbon, and nitrogen. Also 7 mineral elements and 13 trace elements. We also have this thing called isotopes and radioactivity. So notice I said when we do the atomic number, we're talking about the number of protons, because the number of neutrons can actually change, right? So we have this term called mass number, which is equal to the sum of all protons and neutrons in the nucleus. Remember, the nucleus is made up of protons and neutrons. So for instance, oxygen, 8 protons, 8 neutrons. So your mass number is 8 plus 8, which is 16. Isotope is an atom with the same atomic number. That means the same number of protons, but different mass number. So different number of neutrons. So hydrogen. Hydrogen, for instance, has, you can have 1, you can have hydrogen with 2, hydrogen with 3. Notice this mass number is changing, 1, 2, and 3. What does that mean? It means that you're changing the number of neutrons, changing the number of neutrons. Deuterium has 1 extra neutron. Tritium has 2 extra neutrons. Okay? Things that you can change. Radioisotopes, unstable isotopes, they have high energy or radiation released by radioactive decay, which allows isotopes to assume more stable form. So isotopes have different, same atomic number, but different mass numbers, so different number of neutrons. But they'll release that neutron in what we call radio. If they're a radioisotope, they release that neutron and form. Tritium, for instance, is not stable. Tritium is not stable, but it will decay back into back to hydrogen and release those new extra neutrons, and we can use that beneficially. And here's how we use that in nuclear medicine, right? So radioisotopes can be used for cancer radiation therapy. Radiation damages structure of cancer cells, so you inject the cancer cells with these radioisotopes. They shoot off these extra neutrons, release this radiation, which can help kill the cancer cells. You can also use them as radio tracers injected into the patient, and we can actually detect where they travel to, and treatment of thyroid disorders. Nuclear medicine, because those radioisotopes are from the nucleus of the cell, extra neutrons in the nucleus. So it's nuclear medicine. So how does matter combine? This is also very interesting. Section 2.2. All right, so remember we talked about matter, solid, liquid, gases, but it can combine to form mixtures, atoms of two or more elements, which are intermixed without changing chemical nature of the atoms. So if I take water and put salt in it and make salt water, you still have water and you still have salt. You may not be able to see the salt if I stir it up really well, but they haven't changed their chemical nature. I still can taste the salt and I still have water, right? That's a mixture. There are three basic types: suspensions, colloids, and solutions, which we're going to talk about in this section, right? Because this is important. But we're also going to eventually get into the chemical reactions when things do change, like when we cook something. All right, so a suspension, this is going to be very important when you go over the chapter on blood, which we're not doing in this section. It's not till Bio 110, but when we do talk about blood, it's very important to remember that blood is a suspension, a mixture containing two or more components. Large, unevenly distributed particles will eventually settle out. Sometimes people think of salt water like this if you put too much salt into something, but generally I wouldn't think of it as salt water. But if you ever give blood, which I'm going to make my little plug right now, donate blood. It can save somebody's life. If you have to be of weight, a certain weight. I think you have to be more than 110 pounds. I think it is. You have to be 18 years old, and you can't be anemic. You have to have enough iron. Can't be anemic. But if you meet the qualifications, it takes about 30 minutes, and it's an easy way. It's an easy way to save someone's life. So I would encourage you, if you are able, to donate blood. You can do it every 8 weeks. I do it at the American Red Cross. I know that there are organizations out there that will pay you to donate blood. And if you decide to go that route, that's fine as well. Do what works for you. But I know my wife, when she gave birth to our second child, she needed 2 blood transfusions to live. And when you need it, you need it. It's not like you can wait till tomorrow. When you need it right away. So I've donated blood for years. I've been donating blood now for probably almost 20 years. So I recommend it to anybody if you can stand it. And I don't like needles. I'll be honest. I don't like needles. They kind of skeeve me out and make me, I got to look away when they're sticking me with the needle. Those of you all, my wife's a nurse, and those of you all who like needles, not like them, but who have no problem with them. More power to you. I don't like to stick a needle. I don't like doing anything with needles, but sticking a needle in somebody's arm to draw blood, I know it's for a good cause. I just look the other direction, play on my phone or something, and they tell me when it's done. But it's I know I'm kind of a wimp when it comes to that. I can lift 300 pounds, but I can't stand a little baby needle. It's all good. So back to the lesson. So here we have suspension. So blood is a suspension because we have in blood, we have red blood cells. We have that's suspended in plasma. And after you give blood, they actually, you'll see them shake up the bag of blood. Nice red blood. They'll shake it up. And one of the reasons is because blood eventually settles. The red blood cells, which are the bigger particles, will settle to the bottom, and the plasma will be on the top. And so you can actually settle out. That's a suspension, but they shake it up to try to evenly distribute it. You have what we call colloids, which are the best example, as you see here, is milk. Small, evenly distributed particles that will not settle out. If you leave milk sitting on the countertop for an hour, it'll still be milk. All right, so two distinct components, particles small and not visible, but do not settle out. And then we have solutions, two or more components extremely small, evenly distributed particles will not settle out. And that's a substance dissolved into another substance. So a solute, and this is the category we put salt water in. The solute dissolved into a solvent. The solute in salt water's case would be salt. The solvent would be water. And water is is considered the universal solvent, meaning that a lot of things dissolve in water, especially in your body. Right? Extremely small, will not settle out. Right? So sometimes people get solutions and colloids kind of mixed up because they're very similar. Colloids are just small, evenly distributed and won't settle out, whereas solutions are extremely small, evenly distributed, and will not settle out. So they can be kind of confusing. All right. We also have what we call chemical bonds. Matter can be combined chemically when atoms are combined by chemical bonds. Chemical bond is not physical structure, energy relationship, or attractive force between atoms. So what we have here is, first off, is a molecule. And you've heard me use the term molecule probably already in this lecture. Molecule is formed by chemical bonding between two or more atoms of the same element. So oxygen, when it floats around in the air, doesn't float around as a single oxygen atom, smallest unit of matter atom. It actually floats around as two oxygen molecules bound together. So the air that we breathe is actually O2. It's not just O, it's O2, two molecules of oxygen bound together, two molecules of oxygen, all bound together. And that's what we breathe in. When we breathe in oxygen, it goes into our mouth, down our trachea, into our bronchioles, into our lungs, our alveoli, then transfers to our bloodstream, gets pumped by our heart throughout our body, right? That's oxygen. So two oxygen atoms bound together is a molecule. So two atoms of the same element. Now, slightly different is a compound. And think of water, for instance, H2O. Hydrogen, oxygen, H2O, form when two or more atoms of different elements combined by chemical bonding, right? Notice the difference in a chemical bond. If I mix salt and water, I have salt and water both together. If I mix hydrogen and oxygen, chemically, water is different from hydrogen or oxygen. Hydrogen and oxygen are both gases, but water is a totally different matter. It's a liquid. So that now I have changed the chemical structure of the original elements, and so I've had a connection, and now formed this compound. Okay. All right, so this is showing you chemical bonds. All right, this is methane, carbon with bound to 4 hydrogen. This is oxygen gas, I just told you, O2. And what happens in these chemical bonds is they're sharing electrons. As it says here, it's not just physical, it's energy relationships or attractive force between atoms. That attractive force is that they end up sharing or transferring electrons. We'll talk about that. And then nitrogen gas is actually very similar to oxygen gas in that it's 2 nitrogens forming a bond. So what happens? How do these chemical bonds happen? We have chemical bonds are formed when valence electrons, the outermost shell, that's what we call the valence electrons. Remember, we talked about the shells. First shell is 2, second shell is 8, and so on and so forth. The outermost shell is whether it's hydrogen only has 1 electron, so its outermost shell is the first shell. Oxygen has 8 electrons, 8 protons, 8 electrons, so its outermost shell is the second shell. Whatever that element's outermost shell is considered the valence electrons. And so basically we have what we call the octet rule. 8 is the magic number. We want atoms want 8 electrons in their outermost shell. So oxygen, for instance, has, well, in this diagram, carbon has 6 electrons, 4 in its outer shell. Oxygen has 8 electrons, 6 in its outer shell. So it's going to want, since oxygen has 6 in its outer shell, it's going to want 2 more to get to this magic number 8. 8 is considered most stable. Carbon has 6 electrons, 6 protons, 6 electrons. So it has 2 in its inner shell, 4 in its outer shell. So it needs to share 4. So carbon is going to share 2 with one oxygen, share 2 with another oxygen. Each oxygen wants to share 2 with wants to share 2 of the carbon's outer shell electrons, and therefore they all get this, because of the sharing, this covalent bond, we call it. That means we're sharing each other's electrons. We get satisfied with that 8. And this is how we make carbon dioxide, which is the gas that we breathe out, which is made by cells it's actually made by cells as a waste when we're burning energy. And then it's pumped through our bloodstream to our lungs and eventually exits out of our bodies through our nose and mouth. All right, so the oxygen has 6 in its valence shell, so it wants to share 2. The carbon, each oxygen wants to share 2 electrons, share 2 of carbon's electrons to get to 8. The carbon has 4 in its outer shell, so it's willing to share 2 of its electrons with one oxygen, as long as that oxygen shares 2 of its electrons with that carbon, and it's willing to share its other 2 electrons with another oxygen, as long as that oxygen is willing to share 2 of its electrons with that carbon. And there the oxygen gets to satisfy its 8. The carbon satisfies its desire for that magic number 8. Oxygen over here gets 8, and oxygen over here gets 8, and we have a bond, carbon dioxide. We also have what we call ionic bonds. So that was covalent bonds, sharing. Ionic bonds, electrons are transferred from what we call a metal atom to a non-metal atom. And it results in the formation of ions. With ions, we have an ionic bond. So we have a positively charged ion. So what has a positive charge in the atom? The protons, right? So to get a positive charge, we have to have more protons than electrons. So what happens in a cation is one of the atoms is losing an electron. Therefore, it has more protons than electrons. The anion is negatively charged. What has a negative charge? Electrons. So that means it has gained an electron. It has more electrons than protons. And then, so now one is positive charge, one is negative charge. And because they have a positive negative charge, opposites attract and they bond together, that forms an ionic bond. Right, so we talked about this. We talked about sodium. I mentioned it earlier. Sodium and chlorine. Sodium has 1 electron in its outer shell. Chlorine has 7, and it just needs 1 more. So it pulls that electron from the sodium atom. Now sodium has a positive charge because it has 1 more proton than electrons. Chlorine has a negative charge because it has 1 more electron than protons. And because one is positive charged, cation, one is negative charge, anion, they bond together and form sodium chloride, salt. Right, covalent bonds are the strongest bond, 2 or more nonmetals sharing electrons. 2 atoms can share 1 single bond, double bond, or triple bond, depending on how many electrons they share. Methane, you have carbon sharing 1 electron with the hydrogen. The hydrogen is sharing 1 electron with the carbon in each case. So it's designated by this single line. So this line represents 1 electron from carbon, 1 electron from hydrogen, sharing with each other. Double bond means they're sharing 2 electrons each. Triple bond means they're sharing 3 electrons each, right? Those are covalent bonds. Protons attract electrons, known as electronegativity. You know, protons have a positive charge, electrons have a negative charge. It's your electronegativity. An element's electronegativity increases from bottom left of the periodic table to the upper right of the periodic table, right? So we go from here to here, increasing your negativity. Electronegative elements strongly attract electrons and pull away from less electronegative elements, which makes sense. We have this concept also known as nonpolar covalent bonds. 2 metals with similar or identical electronegativities pull with equal force, share electrons equally. Right, so this is considered nonpolar. So nitrogen, carbon dioxide, methane, these are all considered nonpolar covalent bonds, or just your basic covalent bonds. They share the electrons, but you can also have, this is nonpolar, some more electrons spend equal time around both nucleuses. But you also can have polar covalent bonds. Polar covalent bonds are when we have different electronegativities. They share electrons unequally, right, and form what we call polar molecules. So it's not considered ionic bond. One hasn't completely pulled the electron from the other one, but it's considered a polar covalent bond when you have, for instance, in H2O, the oxygen, the electrons spend more time around the oxygen than they do around the hydrogen. So it's still considered covalent because they're sharing, because the electron will spend some time around the hydrogen, but it spends more time around the oxygen. So it has a slightly negative charge on the oxygen end of the molecule of the compound, and a slightly positive charge on the hydrogen end of the compound. So we create what we call dipoles. Polar molecules are partially positive and partially negative ends, right? So and we designate this as here, partially negative. You'll see this symbol here, partially positive, this symbol here, because even though they're not ionic, there's somewhere between ionic and covalent, and we call those polar covalent bonds. The electrons spend a little bit more time around the atom that has a higher electronegativity, the ability to pull the electron a little bit harder than the other one. So it's kind of like we're sharing, but we're not. In an instant, it's going to be spend more time over my house than your house, but we're going to call it sharing. That's the idea. All right, so here is the example that I was just talking about with the water molecule. The electron spends a little bit more time around the oxygen than does around the hydrogen. Therefore, the oxygen atom in the molecule in the compound has a negative charge, and the hydrogens tend to have a little bit more of a positive charge. And that's important because it helps give water specific properties which are important to our body because of that, because it is a polar covalent bond. It also helps things dissolve in water better too. And it gives, so we're going to talk about right here, the hydrogen bonding. Due to this polar covalent bond in the water molecule, we have what we call hydrogen bonds, which are, since the oxygen has a slightly negative charge, and the hydrogens have a slightly positive charge. Now we have bonding between a compound of water with the next one. Each water molecule has a slight bond between positive and negative ends of the oxygens and the hydrogens. And so you have what we call that a hydrogen bond. It gives water its surface tension, which this is why when you put a little droplet of water on like a table, it has like a curve on it. It's because there's little bonds that are happening and doesn't allow the water to just flatten out. If you put like a droplet on, it'll stay slightly curved because there's some bonding going on, pulling it together. That's the hydrogen bonding in the water. And that's a picture of it right there, hydrogen bonding. You can see creates a surface tension, causes blood and water to form different droplets.